Yeah, now you can start telling what. हाँ, जॉब में वार्निंग आएगा. जस्ट शो मी द असेंबली. ये so on the left hand side you have this tree, no, model tree. Yeah, there you go the assembly, there is a plus symbol, so click on that, then click on instances. Yeah, see there are 6 instances, so click on that plus symbol again. So you have imported your part 6 times, that's why you have 6, and all of them overlap on each other. By default वो coordinate system सेम ही रहता है, तो वो एक ही जगह पे डालेगा, तो दिखेगा नहीं तुमको. तो इसको डिलीट करो, 5 इंस्टेंसेस को डिलीट करो. So you can click on 1 4, then shift and click on correct. Now the question is बाउंड्री कंडीशन कौन से वाले पे लगाया है. 1 1 पे लगाया, 1 6 पे लगाया, वो चेक करना पड़ेगा. सो गो टू एंड यू ऑल्सो हैव टू चेक विच वन इज मेस्ड. तो देखो बाउंड्री कंडीशन किस पे लगा है. इसी पे लगा है, ठीक है. अच्छा, अभी मेश में जाओ. मेश भी है, ठीक है. नाउ यू सबमिट, लेट अस सी इफ दैट वार्निंग कम्स. मॉनिटर खोलो, इसका जॉब मॉनिटर. जहां वार्निंग दिखा रहा था ना, वहां पे जाओ. यतिन, आई कैनॉट हियर यू. कैन अदर्स हियर हिम? Avnish, are you able to hear Yatin? मुझे अवनीश भी सुनाई नहीं पड़ रहा. So you guys can hear me? I cannot hear you guys. अच्छा, just हाँ, अभी बोलो. अभी आ रही है आवाज़, ठीक है. सो हाँ, मॉनिटर कर लो. वार्निंग तो कुछ है नहीं. ओपन करके रखो, लॉग में जाओ, लॉग में. तो इनपुट फाइल प्रोसेस हो गया. अभी कैलकुलेशन नहीं स्टार्टेड. नीचे नीचे जाओ, स्क्रॉल डाउन. स्टार्टेड बैक इज स्टैंडर्ड, मतलब नाउ योर जॉब हैज स्टार्टेड, कैलकुलेशन इज स्टार्टेड, सो देयर इज नो वार्निंग. नहीं, तुम्हारा कंप्यूटेशन स्टार्ट हो गया. हाँ, तो वो वार्निंग पहले ही आएगा ना, अगर 6 इंस्टेंस रहेगा तो. सो नाउ यू डोंट हैव दैट वार्निंग. ठीक है. बाउंड्री कंडीशन एंड अदर थिंग्स वी विल डिस्कस टुडे. आई विल मेक समथिंग इन 3D, बट सो फार व्हाट वी डिड. हाँ बोलो. या हाँ बोलो. Okay. So we will discuss partitioning, we will discuss boundary condition on 3D, and I will discuss one more thing today. So for that we should look at the whiteboard. Okay. So whatever we did so far, So we did on axis symmetric model, and same thing we also tried in the last class in 3D, right? But it is the same thing, and we tried it with elastic, so linear elastic, and then elastic plastic. But in none of those cases you should have seen that the sample is nicking. The sample is not nicking, right? So it is just getting elongated. And in the elastic case, there is a Poisson's ratio. In plastic case, the Poisson's ratio is 0.5, volume is constant. And apart from that, nothing else happens, right? So the question is that how can we also simulate the nicking part, and why the nicking is not coming up? So can you tell me why the sample is not nicking in our model? Hello? सुनाई दे रहा है क्वेश्चन? The question is that whatever you have modeled so far, the sample was not nicking. Is this correct? तो क्या मिस हो गया जिसकी वजह से नेकिंग नहीं हो पा रहा है? So if you give values beyond UTS, do you think there will be necking? Right, you are on right track. So just giving the stress and strain values post necking. So what we are doing is, so this is your, let us say, stress strain diagram, and the stress strain diagram, so this is a little bit tilted. Anyway, so the stress strain diagram for metallic material usually goes like this, right? So this is UTS for engineering stress strain. But we have discussed that the way we provide data to the sample is not in the form of engineering stress and engineering strain, but we give in the form of true stress and strain, right? So in that case, our stress strain curve will look something like this. And even if you go beyond UTS, first of all, you cannot get points from here. For true stress strain values, you can't use that relationship, right? So sigma is not equal to S into 1 plus E, and strain is not equal to ln1 plus E. This will not hold beyond UTS because the volume is not constant. So I hope this part is clear to you guys. So this relationship of true stress strain versus engineering stress strain assumes that the volume is constant. That's how you derive these equations. But because the volume is not constant beyond this point, you cannot use this correlation. So that means you can't get the values here. Yeah. One point you can get, which is at the last point, and that last point you get from the experiment. So basically your sample breaks into two pieces. So at the end you join those two pieces and then you measure the final area there, and then you calculate ln A naught by AF, and you get the final, so one particular value of engineering strain there. And then some people, they apply this formula for the stress value and they take that as the last point, so they get only 1 point, and then they extrapolate this data like this. So the point I'm trying to make here is that even beyond UTS, this curve, which is true stress strain, is not supposed to go down. It will always go up, right? And as long as it goes up, there is no reason for softening in the sample for the model, right? So whatever is happening here, Similar kind of thing will keep on happening even beyond UTS, even if you supply the data to the model, right? So even in that case, there will be no necking. So what we will have to do in order to assure or in order to ensure that the sample also simulates the necking of the experiment. So the question you have to ask is that why necking happens in the sample? So can anyone answer why there is necking in the sample? But so you are saying that there will be local anomaly in the stress strain distribution, right? So locally the stresses will be different, where so they are supposed to be of certain value, but locally they will be not obeying that calculation. So why the stresses will be higher at the center or at certain other place? Due to but area is decreasing uniformly everywhere, no? Why area? Stress concentration factor comes when you have a notch or a crack. What is the stress concentration factor? Yeah. So stress at any sharp stress raising place is equal to stress applied into 1 plus 2a by b, where this a and b are the major and minor axes of. So in this case, it is an assumed ellipsoid, which is either a notch or a crack. So here you don't have stress concentration factor. So why the stress will increase at any place locally? Unless there is a local deformation, necking is not going to happen. Okay. So anyways, maybe you need to revisit the MM302 discussion. So what happens is that okay, Vedant, so you have said too many words, and in technical language, those words have certain meanings. So can you tell me what is pressure? No, that is stress. Yeah, hardness also has same dimension, load per unit area. But hardness is not stress. So pressure is one component of stress, which is hydrostatic stress, right? And pressure usually has an opposite sign than the hydrostatic stress. Okay, so hydrostatic stress is mean stress, right? Average of or the mean value of the nominal stresses is hydrostatic stress. And that, so you can imagine a balloon where the air pressure is applied on the surface of the balloon from inside to outside, right? So that is a hydrostatic stress example. And the opposite of that is like when you put a ball inside water, so then the forces are on the surface of that ball, right? And the forces are always normal to the surface of the ball and they are squeezing. So that is pressure by definition. Okay, so that is negative hydrostatic stress. Okay, so the material will flow Okay, so you have set a right point. So this is the cylindrical parallel part of the tensile specimen, and when you have applied forces so that you are pulling it, so the material is flowing, and for certain period of time it will flow in the uniform fashion, because there is no region to not flow uniformly unless you have something which is inhomogeneous inside. So it will elongate following the Poisson's ratio or constant volume condition, right? But it cannot do that for ever. So at some point of time it will become very thin, very thin, right? And when it becomes very thin, there will be a local anomaly at some point. It can be center, it usually is center for ideal condition because of the constraint. So where the constraint is maximum, the constraint is maximum at the center, right? Because you are pulling from upside and downside, so where the forces will balance each other, they will balance at the center, right? And that's why you have to have the anomaly there. So there will be a breaking point where the continuum cannot sustain any holes. At some point of time, the continuum will break. Okay, so there will be a surface creation. Once there is a surface creation, what happens? The stress will change and the strain will change locally. So then you will have those stress concentration factor and all those things. But that is a very ideal situation. Usually what happens is that if the material is flowing like a ductile material, then you will have some void formation. Okay, so these voids are the points of breaking of continuum. What is a void? Void is something where you don't have a material, right? So continuum is not there. And why they form? They form because locally at that point the material is no longer able to take the stress larger than what is already there, or the strain larger than what is already there. So what you can do is you can imagine many small tensile samples in one tensile sample. Okay, this is also like finite element analysis. So if you just hypothetically break this tensile sample into smaller tensile samples, and imagine one of these small tensile sample which is also seeing same kind of force, but apart from these kind of forces, it is also under the constraint from the sides. Okay, so the constraint from the sides are that this tensile sample has to be connected with the adjacent one, right? It cannot act freely from the side. So that is the constraint which it has to follow. But at certain point of time, it cannot do that anymore, right? And then there will be separation, and that separation, you can imagine that to be as a micro void. So these micro voids are forming, and then they will grow in size, and then they will join each other, and they will become a big macroscopic crack, and after that the phenomena of failure will start. Is this part understood? So in our finite element analysis, we have told material points to behave in certain equations, and one of those equation in simple word is that as long as you are in elastic domain, you follow this, and when you are in plastic domain, you follow something like this, right? So we have defined to the material that how locally the stress or strain, and at what point of time the stresses should be following a different law than these, right? So that means we have not told the simulation that at what point of time the void will form, and at what point of time the model should know that that part of one element cannot hold the stress strain rule anymore, and it has to just go out of the system. So the finite element model has to consider one element gone, missing. When will that happen? So those information we need to tell the model, and only then it will be able to simulate the thing which we are talking about, and the name for that is damage. Okay, So although it's a concept, I mean the reality is that there is no continuum there. As soon as a void forms, that void does not have the material, so the continuum has broken. But we, in order to make things easier for finite element analysis and calculations, we have to do something so that we remain in the continuum space, and we still can incorporate this discontinuities in the system. So we have to do some kind of trick, okay? And how can we do that? One simple idea is that you assume a box, okay, in 2 dimension, and you are applying certain amount of force, and this has an area, so you have stress is equal to force per unit area. So stress is equal to force per unit area, and so everything is good. What will happen if there are voids in the system? So let us say there are certain number of voids in the system, and they can be of different sizes, they can be of different shapes, we are not bothered about it. So in that case, if I cut it at one place and then I try to find out that what is the stress there on this plane, okay, on xx dash plane, then that will be force divided by the area of xx dash plane, right? And you can see that this area is not equal to this area, right? Because if we look at this plane closely, then we will be cutting certain number of voids, right? So the total area A is this, but the real area should only include these parts, right? So this is A dash and this is A. So obviously these two are not same. Is it making any sense to you? Okay. So now I will assume that in a way of defining this difference in area, I will call that by a parameter D, or let us say omega, okay? And I can say that obviously A dash will be a little bit smaller than the initial area by a factor omega, okay? So when omega is 0, then A dash xx dash is equal to A, and whenever omega has a value higher than 0, then obviously this will not be true, so it will not be equal to that, but it will be equal to A into 1 minus omega. So okay, and then to what maximum value it can go? Obviously it can go to a value of 1 where the area will become 0, right? So when omega is equal to 1, Axx dash is equal to A is equal to 0. Well, not A, but A dash xx dash will be equal to 0, right? But we cannot reach that extent ever. So that is so why we cannot reach that extent? Because before we reach to a place where all of the surface is consumed by voids, the material will fail much before that. Do you understand this? So you have an area where certain voids are there, right? And then with more stress, the number of voids or the size of void or both of them will be increasing, right? So gradually your A dash is decreasing with as the force increases, the A dash will keep on decreasing because you have more number of voids and bigger voids, right? But you cannot go to a point where the whole area is consumed by the grown up void or crack, if you call it. It will not go to that point because material will fail much before this condition. Okay. So is it making any sense to you? Okay, so what we have established is that we have a parameter omega which starts from 0, and ideally it can go to a maximum value of 1, it cannot go beyond 1, that is understood, right? But in reality it will hardly reach the value of 1, right? And this defines how much difference in stress I am getting, okay? So you see that there is a change in area and therefore there is a change in stress, right? So the real stress when there is void formation will be equal to force divided by A dash, which is A into 1 minus omega, right? And F by A is simply the stress which you have on the continuum material part. So this becomes something like this, right? So F by A is sigma, and then you have this factor, right? So what is happening now, you see that because of void you have certain amount of applied stress, but locally the stress is increasing because of this factor. Is this making any sense to you? Yeah, yes. So we have defined a parameter which is incorporating the effect of voids, right? But we are not actually going to simulate voids. We are just going to tell the conditions of this parameter omega in the element, that at this point of time omega begins and acquires value higher than 0, right? So on stress strain diagram we can say that as long as the material goes like this until UTS, or we can start at any other point, but we have to be in plastic region. So we can say that, let us say at this point of time, before this the value of omega is 0, so everything goes cool, okay, no problem. As soon as you cross this point omega starts, right? And then all this calculation of local stress based on the factor value of omega, you know, starts being accumulating in the element. And then in each calculation, because then the next time again you will strain a little bit more, right? So if you are here at point A, so let me make it a little bigger. It can be UTS, it can be a little before UTS, it can be yield strength. It depends what kind of material you are trying to simulate. Okay, so if you are at point A and then you are going at point B, what you actually are doing is you are extending the sample or the element, right? So you are applying more strain, right? So if the strain is increasing, when the material point goes from A to B, the stress will also increase following whatever law. So elastic plus plastic, and this factor will be also in the calculation. So here the omega value will be higher than what was there. So omega A will be lower than omega B. So the value of omega will keep on increasing. Okay, and now you try to visualize this, that actual true stress strain diagram was going something like this, right? It was going up and up always. But this and how that will go up and up, because omega is increasing the value of stress every time, right? But the total load bearing capacity of the material will be going down. Why? Because omega is increasing. So the same reason for both of them. So engineering stress strain diagram will be going down, but true stress strain diagram will be going as it goes, because the stress is increasing and without doing anything stress is increasing. So this stress is increasing not because of strain hardening, not because of some real hardening in the material. This is increasing because of the decrement in the area decrement in the load bearing capacity of the material. It actually is a volumetric phenomena, but we are simplifying this looking at the area. Okay, so this actually void is, I mean everything is in 3 dimension. Okay, so using this simple idea, we can tell the model that you do this, you apply this factor in your calculation, and then you do the calculation. And so for that we have to tell that this is the initiation point. So let us say that at this point of strain, so as soon as in one element your strain value reaches a certain strain value, critical value epsilon c, as soon as it is greater than equal to epsilon c, omega is greater than 0 or greater than equal to 0, right? So whenever it is a little bit greater than epsilon c, omega will be greater than 0. Okay, and depending upon how much strain you have, omega will be acquiring certain value and it will keep on increasing, and at certain point of time omega will be reaching its own critical value when you say that this element now is broken and remove this element out of the system. Okay, as I said, omega ideally should reach a value of 1 when area becomes 0, but it will not go there. So omega will reach a critical value of omega. When that happens, then you say that this material is no longer good to hold any load on it. So you can imagine what can you imagine? You can imagine a wax, a candle, and in that candle, so this is a candle, and in that candle you put needles and make a lot of holes. Okay, so you make it porous, you prick it and you create n number of holes, and you keep on increasing the number of holes. So do you think you have to make so many holes so that the whole candle goes away in order to break the candle? So you obviously don't have to reach that point, right? So at some point it will be so weak that it will just shatter, right? So you are not really going to maximum value of damage, but you are going to a critical value of damage where the material is no longer able to take the load. Okay. Okay, so and the same thing will explain you what is known as stiffness degradation. So if you look at the stress strain diagram and the engineering stress strain diagram, so if you unload at point A and point B, if you unload, it follows the same slope as it is there in the initial condition, and then you reload it and then you again unload it, it will follow the same slope because the material is intact, it is continuous, so the stiffness is same. But when the stress strain diagram starts going down towards the failure and then you unload it, the slope will change and it will keep on changing and it will keep on getting lower and lower. Okay, this is not the real elastic modulus of the sample. Because the material is damaged, the material is lost, right? So there are too many weakness in the material, and because of that the load bearing capacity, which is described by the slope, right? For certain increment in the strain, how much increment in stress is required, that is what is the stiffness, right? So in order to increase the strain by 0.1%, you need certain amount of stress. And that amount of stress value decreases because the material has become softer. Why it has become softer? Because it has become weaker, because it has become porous, it has a lot of voids, and so this slope will keep on decreasing, right? And if you call it E, then E will remain E until here, and then it will change a little bit. Okay? And this change, so this E dash is smaller than E. and the same parameter will be, so E dash will be equal to the real elastic modulus into that factor of damage. So this omega, yeah, the factor will remain same. Okay. So this omega is called damage parameter. Nothing fancy about it because it is describing damage. And then damage starts, so that is called damage initiation. It starts at certain point. Okay, it starts when the strain. So we can put n different criteria for different types of material, but basically if you imagine the small pieces of this sample to be smaller tensile samples, so then you can hypothetically say that each small tensile sample has its own failure strain, okay, has its own UTS. So after UTS, you can imagine that those smaller hypothetical samples are softening, or they begin to soften, or they begin to neck. So you can say that the damage starts when the strain value is some value. So let us say 0.2. Okay, and then after that the omega has to follow certain rule, so that omega also keeps on increasing with the time of, with the value of strain, right? So as the strain increases, omega increases, but is it increasing linearly, or is it increasing following certain polynomial function? So what is that function? What will describe that how omega, or what is the relation of omega with the strain or with the stress or with any other parameter? So that is called damage evolution. Okay. So damage evolution basically will describe how omega is a function of strain or strain rate or stress, temperature, constraint, etc. Strain rate that I have already given. Okay. So it can be a function of all those parameters, and that function will define how omega follows, how it increases, and then you have damage initiation, damage evolution, and then you have failure. So failure criteria will be when omega reaches omega critical, we define that element has broken, gone, remove it out of the system. Okay, and this is how we tell the model to do this. Okay, so usually it has been found from experiment and a lot of study that this damage parameter is usually a function of strain rate, and it is a function of constraint. Okay, so meaning what? That if at this tensile sample, these hypothetical small babies, if they fall in the middle somewhere, here, and if you take some at the surface, or if you take something here, they will not follow the same criteria of damage initiation and damage evolution, because the amount of constraint on 1, 2 and 3 are not same. So 1 is facing side constraints from both sides, 2 is not facing from one side, and 3 is at a place where the constraint is a little different from what you have at the center, right? So these also are related to the damage parameter, and therefore usually it is a function of strain rate and the constraint and the amount of constraint. And then you also have to tell this that do all this calculation before you reach the failure strain, obviously, right? So when you reach failure strain, there cannot be any damage evolution, it will just break. So failure strain is related to the critical value of omega c, right? So far are you good? Do you understand what I'm saying? Okay. So, we will do this and we will see that if our sample necks, if it necks, then the next task of ours will be to take an experimental stress strain curve from any article available on internet and then simulate that using this damage formulation and see if we can get that stress strain behavior by our own model. Okay, so we have to somehow hit the right damage parameter so that we can simulate the damage. Okay, so in order to do that, it is so in order to simulate this thing, or in order to fix the damage evolution criteria, the real way is to conduct a lot of tensile testing. Okay, and how will you ensure that the tensile test which you are doing is at a constant constraint value? Okay, because it's a function of constraint. So from one tensile test, how will you find out that at which failure strain or at which strain the damage starts to begin or the material starts to neck? Because once you neck, the constraint has changed, right? So the ideal way of doing that is to test a lot of notched tensile tests. Okay, so instead of parallel gauge length, you make a notch in the sample, and this creates a stress concentration factor which will be constant if you have constant B value and constant A value, right? So you will have this 1 plus 2A by B. So 2A by B, 1 plus 2A by B is a constant factor, and then you create different samples with different ratios of A by B so that you reach different values of constraint, and for different constraint values you find out the values of strain rate. So you fix the strain rate also, okay, and then you find out that at what strain the sample fails. So you get the point like failure strain for a sample which was tested for A and B value, some value, and it was tested at a strain rate, certain strain rate, and then you conduct 5 to 6 tests there and you keep on changing A and B, keep this constant for 5 samples or 3 samples. So if you test more, you get more data points, right? So EF2, EF3, EF4 and so on. So this is how you get the experimental results, and from that you establish a formula and then you feed it to the model so that your simulation is more realistic. But you can imagine that in order to simulate one tensile test, you have to do so many tensile tests. Okay, but the labor is not bad, because if you do this much of tensile test and once you establish this formulation, then for this grade of material from which you have made the tensile sample, you will never have to do these kind of tests again. So if you want to find out component failure, or you want to find out something else, then you don't need to really do the testing again and find out how the damage happens. You can simply feed that formula and use it, as long as the material grade and heat treatment and all those things are unaltered. So grain size and other things. Okay, also rolling. So there should not be any preferred orientation. Okay, which is in a way related to grain size. Okay, so this is what we are going to do. And to make it simple, let us assume that our damage evolution criteria will not be a function of constraint, which is a very bad assumption, but let us make that assumption. Okay, so if we plot the damage parameter versus constraint, and that is independent of constraint, then what will happen? It will be a constant line, right? So for any value of constraint, it will always have the same value, right? So this is what we have to put, and we will not assume that it's not a function of strain rate. So we will give some value of strain rate, and we will just see for our modeling and simulation lab experiment how it goes. Okay, so now let us come back to Abacus and let us try to model the thing in 3D, and there we will also see at boundary condition, and what other thing was there? Partitioning. Okay, so oh, I am not sharing. Am I sharing the screen? So let me share the screen and let me go. Where did I make the work directory? I believe here. It was real answers and then session 3. So let us make damage and okay. Okay. What am I doing? Oh, I have to first save this now. No. Yeah, go on. Take it. Done? Okay. Okay, so I should open. So where is, and here we have the okay. So now let us begin. So, or I could import the models. No, let us do it like that only. Okay, so let us make it in 3D. So 3D deformable extrusion. You can also do revolution. I think we can do revolution. I have never done it, but let us try this revolution. So for revolution, I will have to make a square which will have radius. How much was the radius of our sample? Radius था कि diameter था? अच्छा 4.5 and gauge length? Okay, so rectangle बना दिया. Now I have to revolve this. So I will have to revolve it by 360 and no pitch. Okay, So this becomes a cylinder. It works, right? And the same thing you can do by extrusion also. So instead of going to revolution, you go to extrusion. Then you make a circle and extrude it, right? So in this case, the radius of the circle will be 4.5. And we have to extrude it with 22.5 say, तो भी cylinder बन जाएगा. So you can make it in both ways. And what if I take, so revolution, you know now what it is. So in revolution, if I make a circle like this, right, and then fix the diameter by whatever value it has, and then done, and then I want to revolve it by, let us say, 3600 degrees. That means 10 revolutions, and then I include a pitch of distance per revolution is, let's say, 2, and then I say OK, then it will make a spring of this kind. So this is what revolution is. It's overlapping because our diameter was 3.54 or something, so pitch should have been much higher. So we don't need these two things. So we have this tensile sample ready, and now we have to make property. Oh, actually you can make either half of this tensile sample, or I can still cut it in 1/4 and I can just model that because it is symmetric that way also. So what I mean to say is, instead of making the whole circle, I just have to make 1/4 of that circle. So this was 4.5, and then I will cut it. And I just need this 22.5, and this is what I can model, okay, because this is also symmetric. Okay, so this is actually 1/8 of the total sample. Yes, Satya Prakash, you have raised your hand. Satya Prakash. Oh, no issues. Okay, so now we have made the part. We go to property and we have to make that material thing, and here we have to give those properties of damage also, which we will do. So what was our Young's modulus in our last simulation? Let us see in the input file. Yeah, 200,000, 0.3 megapascal, and this is the plastic data. Okay, so 200,000, 0.3. Then we go to plasticity, and I have to give these values of stress and strain. Control C, go to Excel, Control V, text import to wizard, delimited, comma, finish, Control X, Control V, and Control C and Control V. ठीक है, तो डेटा आ गया प्लास्टिक का. Now I have to define damage. So we go to damage. So there are different ways of defining damage for fiber reinforced composite, elastomers, blah blah blah. So I'll go to ductile damage. Damage for ductile metals. There also you have different formulations given by different people. So we go to ductile damage, and As I said, it's a function of failure strain, stress triaxiality, which is the constraint value, and triaxiality is defined in terms of the hydrostatic stress versus equivalent stress ratio. That is the definition of triaxiality for this case. If you know you are not sure for something, no, if you think that, oh my god, what are these parameters and how should I fill it, then you simply go to the internet, and our friend Mr. Google should help us. So google.com, and then you go and just write ductile damage abacus manual. Yeah. तो ये जो इसका विंडो पॉपअप होता है उसके लिए वापस आना पड़ेगा. So how much was 1920? Okay, no, keep changes. हो गया. What is the screen size here? You can't see the screen size. Anyways, so क्या कर रहे थे? हाँ, Google. So all these are abacus manual. You usually have manual when you have the software also. So damage evaluation, you can go there. Defining damage and failure ductile metals. Let us go and see. So here this is abacus manual, and we are in damage and failure for ductile metals, and then we have damage and failure for ductile metals. So this is talking about ductile damage initiation, evaluation, and all those things. And you see this formula where omega, instead of omega, can you see this formula? Sigma is equal to 1 minus d sigma bar. Can you see this? Yeah, so this is how they also use the same formulation. And you have to see the CAE usage. So damage initiation, and the formula changes a little bit. It takes the form of elemental integration in 3 dimensions, so we will not go there. Input file usage, we have to go to abacus. So these are other models, Johnson-Cook model and other. So we have to see where so this is theory. We have to go to the CAE manual instead of going to user manual. Let us go to CAE user manual, and there. So working with abacus models, files, creating and analyzing using modules, engineering and modeling techniques. I believe it should be here. No. So step module, property module. In property module we have what? Defining mechanical material model, and there we have damage. So, and there we have ductile damage. Okay, and so you see stress triaxiality is defined as eta is equal to minus P by Q. So minus P is actually pressure, and negative of pressure is hydrostatic stress, and Q is the equivalent stress or von Mises stress. So it's the ratio of that which describes the triaxiality. Strain rate is basically the strain rate, so plastic strain rate, it's not counting the rate of change of elastic strain, and then you can make it a function of temperature also and other things also. But basically you will have strain rate and stress triaxiality. These two are going to be the parameters which you have to define, and you may need to expand the dialog box to see all the columns in the data table for detailed information how to enter data, see entering tabular data, and you can go anywhere and see if you have any problem. So using the property module toolbox, and let us say you wanted to know how to define the stress strain data in the plasticity. So you go to define plasticity, define metal plasticity, and then you can see what is yield stress, what is plastic strain, what is rate, temperature, blah blah blah. Okay, so if you want to know anything, then you can check on this manual. Don't have to read all of them, but go to the right place and then you will see what it means. Okay, so coming back here, and we have to give some value of failure, fracture strain. So what was our stress strain curve? We must have had some stress strain curve to begin with. So this is elastic plastic. So our stress strain curve looks like this, right? What is this? Is this only true stress or what? No, this is engineering stress and engineering strain, and starting from where? 214. Why? Because we are starting from yielding. Yeah. Okay, so which one is it? This one? But this is not starting from yielding. Why? Oh, 2 and 3. It is starting from yielding. Fine. So failure strain is the last point, right? And this is the total strain. It's not the plastic strain. So what is the value? It's 0.3. Okay. So 0.3 also includes the elastic strain. So we have to actually remove that elastic part. So it should be 0.3 minus elastic modulus, stress divided by elastic modulus, and the stress here is, so we have to actually look at 446.885. So 446.885 divided by 200,000, and that is 0.2977. So this is actually 0.3 only. 2977 is also fine. So fracture strain value is 0.3. Stress triaxiality value, so that we have to see. Strain rate value, so we will give some value of strain rate. So usually how do you calculate strain rate? Do you know how to calculate strain rate? So we know that this is actually rate of change of plastic strain. It is not the total strain rate, right? Plastic strain में कैसे change आ रहा है? That is what it is. But strain rate, so this is an assignment, right? So if let us say you are doing, so you conduct an experiment. So when you do an experiment, you define a rate so that the sample is pulled in certain rate, right? So usually that rate is 1 millimeter per minute or 0.5 millimeter per minute. From that, how do you calculate strain rate? Okay, so that is a very small calculation. So you should be able to answer this in the next lab course, and I mean you can put it in your lab report. Okay, so just note it down. For certain value of pulling rate in the machine, how do you calculate the strain rate? And I'm not talking about plastic strain rate, but here you have to give the value of plastic strain rate. So I'll just give some value, 4 e to the power minus 4. And as we discussed in our whiteboard when we were discussing damage, so if you look at the whiteboard, so are you looking at the whiteboard? Okay, so there, if you want to make it independent of the the constraint, then you basically give one value of your parameter. So here, instead of damage parameter, I am trying to make the failure strain independent of the constraint, right? So I will give two different values of failure strain for any two different values of, same value of failure strain for any two different values of constraint. So then it will become independent of it, right? Are you getting it? Okay, so that is what I will do. So let us come back to abacus, and here I want to make this fracture strain independent of stress triaxiality, right? So I'll give a value of stress triaxiality 0, okay, and then I create another one, same fracture strain, and give a stress triaxiality of 200, and strain rate I can give, let us say, a little bit higher, no? So 4e to the minus 3. Okay, so it is a function of strain rate, but it is independent of stress triaxiality. Okay, is this okay? Okay, so now I have defined some damage here, and rest of the things are okay. So I click OK. So material has been made, and then I have to assign this material to this guy. I'll take this. Done. Oh, so some window is popping up which I cannot see. I have to make a resolution back again. So create, this part you already know, so just let me do it. To create a section, homogeneous, solid, continue. There is no need of plane stress, plane strain thickness because we are defining all the dimensions in 3D. Okay, it became green, so material has been successfully. Am I sharing the screen? Yeah. Okay. So material is defined, described. Now, what do I have to do? I have to bring it in assembly. So I click this. I have two parts. I have made two parts. I have to check which one I have actually assigned the material to part 1. So part 2 there is no need. Oh no. Part 1 को दिया क्या नहीं? Property part 2 को दिया ना? Yeah. So part 1 I will delete so that we don't create any error. So property, assembly, go to assembly. So part 2 is coming already there, and it is dependent, so I will make it independent, and then I go to step, I will create a step. And what was our step criteria? Step was, so 0.011, okay, what is 0.05? Okay, oh, 0.05 is maximum. Okay, so general static, non-linear geometry on कर देते हैं, and initial is 0.01, maximum is 0.05, this is 9, this is 1000, and everything is okay. Done. Step is created. Now go to interaction. We don't have to do anything in the interaction module. We now have to provide the boundary condition. So boundary condition जिसको देखना है वो देखिएगा. Okay, so I think it is big enough, no? I don't need to change resolution, no? You are able to see the model, no? Okay, so let us come back to the whiteboard again, because we need to discuss something here, no? So whiteboard. Okay, so are you guys looking at the whiteboard? Okay, so here what we have to do is, so this is our total big tensile sample which we have cut here. So we have half which is symmetric on this plane, then we cut it like this. So this is how it is. Right, so the lower plane is still symmetric. If this is x, y, and Z. So this plane and this plane which is on XZ plane. So XZ plane पे symmetry है इसका, ठीक है. Then this part, this plane is symmetric on which plane? This is symmetric on YZ plane. So this plane. Okay. So YZ plane पे symmetric है. Then इसको और काट दिया. So now we have something like this. So ऐसे तो नहीं बनेगा. So we have something like a watermelon. So ऐसा है. So ये वाला part YZ पे symmetric है. YZ, right? और इसको काटा उधर. So that is symmetric on this plane is symmetric on XY, right? तो हमने इसको actually 1/2, then उसका half 1/4, 1/4 का 1/8 कर दिया इसका. Okay. So we have to apply that kind of symmetry. We have to apply YZ symmetry there, XY symmetry there, and then on this plane we have to apply symmetry so that the other half downward sample, so this part is taken care of, and that is what we have to do. Okay. So let us go back to model. Okay. So we have to go to boundary condition, create boundary condition. So first boundary condition is gonna be symmetry, continue. So ये जो है, can you see the cursor? Can you see my cursor? Okay. So ये on this plane something is there on the other side also, right? So in which direction it is? It is in the X direction, so we have to supply. So symmetry, continue, take this plane, done, and then this is symmetric on X axis, that will apply X symmetry, done. Then create symmetry, you have to take this plane, and that is symmetric on Y axis, so Y symmetry, and then you have to create symmetry, continue, and we have to take this plane which is symmetric on Z axis. So symmetry, 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 symmetry हो गया, ठीक है. Now we have to apply load also. So we applied load or displacement? I think we applied displacement. No, boundary condition 2 millimeter. Okay. So ये side symmetric है, तो उस side पे we have to apply the displacement. So we go to displacement, rotation, and take this plane, done, and Z axis में जाएगा वो 2 मिलीमीटर अप जाएगा, बाकी कहीं कुछ नहीं जाएगा, बट रोटेशन हो सकता है. So U1 U2 नहीं देना है, so U1 U2 0, U3 2. Okay, so this is what it looks like. Okay, so our boundary condition are done. Now we have to go to mesh, and when it looks green in abacus, by default it is structured. The algorithm is structured. That means ये ऐसा क्यों दिख रहा है? Yes. So okay, so we go to mesh type, and here we have to apply 3D stress. That is okay. Standard is okay. So that means implicit algorithm, shape function is linear. So this is a brick element, 8 nodded brick element with reduced integration R class and blah blah blah. One thing which you have to ensure that deleting of element is on. Okay, so element deletion you have to click on yes, and maximum degradation is the value of omega. वो ओमेगा 100% जाएगा नहीं, ओमेगा 100% तो नहीं जा सकता. So if you say that at 90% of omega the element should be considered as fail, so you just write 0.9 here. Okay, so instead of 1 it will go to 0.9, and this is the element type. I will draw this element on whiteboard and will tell you how it looks like. So done. Okay, and then I have to change the resolution so that we can look at partitioning. because before meshing we have to do some partitioning there. So $1720 तो कम हो गया, 19,20,080. Okay. So what do we have to do now? We have to partition this thing. Okay. So view toolbar, views, isometric is this one. Okay, good. So now we have to do meshing. What I want to do is, I'll explain that on whiteboard. So let us go back to whiteboard for a while. So can you see the whiteboard? Okay, so what we want to do now is we have to partition, and before that it said C3D8R. This was the element type, right? Element type. C3 means the space, it defines the space in nutshell. So this is 3 dimension. Then D8 is number of nodes. R means reduced integration. Reduced integration simply is a numerical integration procedure which we will learn in our theory class. And in that process what happens is that the dimensions of numerical integration, the number of points. So numerical integration is not this kind of integration. Numerical integration means adding up small pieces. Okay. So an ideal mathematical integration, when that is converted to a numerical integration. So what is numerical integration? So let us say you want to integrate dx from 0 to x, right? So this is simple analytical formulation. Okay, so there is no issue there. Numerical integration means that you plot x like this. I mean f of x. So f of x dx. And what you do is you take small dx's and you add all those. That is what basically integration is, right? So instead of doing analytical integration, the numerical integration just adds the small pieces. But the problem is that you don't have all the pieces. Okay, so you have to make certain assumption, and then you have to take, you know, good amount of pieces and add them and then give the value. So it will never be exactly equal to analytical, but it will approximate. So it is like finding the area of a of any function by using Simpson's rule or trapezoidal rule. Okay, so that is what it is. So trapezoidal rule is also kind of numerical integration. So yeah, so if you have to take so let's say n number of points and somehow you can reduce it to half of that, that is called reduced integration. Okay, is this understood? Yeah, you will create more error. Yeah, that is true. Come again. Yeah. Yeah, that is true. Yeah, that is true. So reduced integration you use when you assume that. So why do you want to reduce the number of integration points? It is basically नहीं, रियलिस्टिक के लिए तो ज़्यादा नंबर ऑफ इंटीग्रेशन पॉइंट लेना पड़ेगा, कम क्यों लेते हैं? ज़्यादा इसलिए चाहिए कि तुमको इसके अंदर जितना पॉइंट मिलेगा यू आर रीचिंग द रियलिटी, है ना, यू आर रीचिंग द एनालिटिकल वैल्यू. कम करने से एरर हाँ या दैट्स व्हाई यू वांट ज़्यादा, बट द क्वेश्चन इज व्हाई यू वांट लेस. तो द सेम आंसर इज सिमिलर. like if you remember our discussion on shape function, no? So you have two nodes here and you are linearly interpolating the degree of freedom between this node and this node, right? So this is a linear shape function. Yeah, I am in class, I'll call you later. So you can make it better by creating one node and the middle, right? And then it becomes parabolic. तो डिग्री ऑफ पॉलिनोमियल जो लीनियर था, एक लाइन था, वो पैराबोला हो गया. पर इससे प्रॉब्लम क्या आया? दैट इंस्टेड ऑफ हैविंग 4 नोड्स नाउ यू हैव 8 नोड्स. ठीक है. सो ये जो अब मैट्रिक्स बनेगा डिस्प्लेसमेंट का, इफ यू ओनली हैड 4 नोड्स यू हैव u1 v1 u2 v2 u3 v3 u4 v4 is equal to stiffness matrix into force. So F1 Fx1 Fy1 and Fx4 Fy4. ठीक है, ये कैलकुलेशन होगा लीनियर शेप फंक्शन के लिए. बट अगर इफ यू क्रिएट 8 नंबर ऑफ नोड्स, व्हाट हैपेंस? इसका साइज हो गया डबल. सो दिस विल गो टू u8 v8. This will go to fx8 fy8. So you need more physical memory, you need more calculation to be done, right? So RAM का साइज ज़्यादा चाहिए होगा. एक एलिमेंट के लिए कोई इशू नहीं है, 30,000 3 मिलियन एलिमेंट्स है, सो सीधे सीधे साइज डबल हो रहा है. स्टिफनेस मैट्रिक्स का साइज क्या हो रहा है? सो इनिशियली इट वॉज 4x1 4x1, हो गया 4x4. Right? If you just create middle node, then it becomes 8x8. ठीक है. अब 8x8 मैट्रिक्स को तुमको इन्वर्ट करना है. At some point of time you have to take an inverse, right? So inverting a matrix by using Gauss elimination, तो lower triangle को zero करते जाओ, that is very computationally consuming, right? And then just to create space, so but there is a trick to avoid क्रिएटिंग 8x8 मैट्रिक्स. यूजुअली क्या होता है कि ये जो स्टिफनेस मैट्रिक्स होता है, इसमें मेनी ऑफ द पॉइंट्स आर जीरो, अ लॉट ऑफ मैट्रिक्स इज एम्प्टी. ओके, सो देन यू इंस्टेड ऑफ क्रिएटिंग द होल 8x8 मैट्रिक्स, यू क्रिएट स्पार्स मैट्रिक्स. ठीक है, वी विल नॉट गो टू कोडिंग पार्ट. सो द पॉइंट इज दैट you can attain more accuracy by making it more complicated, but then you have to take a call that whether if you can go to that if you can deal with that computationally heavy computation or not. So if you have a good machine, if you have all the time in the world, you go for accuracy, right? So usually the discussion is, do you want to make finer mesh or do you want to create a higher order shape function? But the better would be to create a finer mesh of higher order function, shape function, right? दोनों ही ज़्यादा कर दो, पर उसमें तो it will become very very heavy. So if you can afford to do that, why not? But if you cannot afford to do that, then you have to be happy with whatever more or less good results you are getting. Okay, are you getting my point? So it is, what you are saying is right. You do the full integration. Full integration, good. Can you do it? If not, then reduce it and deal with the error. The Simpson's trapezoidal rule जो होता है integration का, there also if you create more number of points, then you get a better result, right? But if you can do that computationally, then good. If you can't do it, then you have to be happy with less number of points, right? So this was the element which I wanted to tell, and then I wanted to tell why we are going to partition. So this is our watermelon shaped tensile sample, and usually at the center of the tensile sample, so ये tensile sample है, and at the center you have damage and so where will the damage start? Damage will start usually at the center and then it will grow towards the side, if you want to calculate constraint and all those things. So important area is this towards the center. Here towards the edges, not so important. So again, why we are doing this, we can make the same element everywhere and we can make the same size of the element everywhere. Yes, we can do it if we have good machine, if we have all the time in the world. If you want to reduce our computational time, then we have to focus on those areas where we need refinement and those areas where we can be happy with bigger elements also. So at the edges we can be happy even if the elements are not so regular, not so small. But at the center we have to keep it fine, keep it small, keep it accurate, right? So that's why we need to do a little bit of refining at the center. And for that I will create a small partition, and in this part I will make smaller mesh, and in the above part I will gradually transition to a bigger element size. Is this understood? Okay, so let us go to our model. Okay, so are you now looking at the screen of model? Okay, so we can do partition in the part module or in the assembly module. At any place we can do. And your question was how to do the partitioning in 3D, because there we used to do it by face. Here, you know, instead of face we have a volume. So the simple thing is that you partition a face, then extrude it through a volume. How did we make the 3D thing? We make the 3D thing by making something in 2 dimension and extruding it or revolving it. So similar thing we will do in partitioning also. We will cut one face, extrude it towards one edge, and we will do the partitioning. Okay, so where you see this datum coordinate, there we have defined the symmetry. So that is our center part, this is our edge part. So I have to make a partition closer to that center part. So I click on this one. So this is partition face sketch, this is partitioning cell. Before partitioning shell, I will have to partition face. Okay, so if I click on partitioning cell, then you have these options: point and normal, 3 points, and normal to the edge. Okay, so I will come back to this, but before that let me partition a face. So I'll partition this face. Sometimes if the geometry is very complicated, it is not possible to follow one way of partitioning. That's why you had 3 different ways of partitioning. So I want to first partition this face, and for that it is asking that you give me an axis or an edge which is vertical and on the right hand side. So this edge is vertical and on the right hand side. So I click that and I go on that face. So this is my center part, this is my edge part. So I want to create a partition somewhere here. So it is 22.5 altogether. So I'll make a partition at 5. I can make more partitions also. I can make it a little complicated also. So let me make 2 partitions. So one partition is from the center, it is 5 millimeter away. I want to make, so this is 3, I'll make it 5. 5 is too much, so I'll make it 2 millimeter. Apply, and the other one I want to make it at 5 millimeter. So this is 5. Okay, so done, and you see a partition has been made. Now I will create a cell partition by extruding something which I have created in 2 dimensions, which is my face partitioning. So I will extrude this thing. Okay, so I click on this option, extrude sweep edges, select one or more edges. So I'll select one, this one. I want to extrude along which direction? Along an edge direction. Extrude along direction means XYZ, or along edge means you take an object on the part which I have made. So I'll take this edge and I want this line to be extruded along this edge, if you can see this arrow, okay, and then create partition, and that partitioning has been done, okay. If you see, this part has been partitioned, okay. So similarly I will do this one. So extrude, sweep and edge. So now instead of one cell, that means 3-dimensional volume, I have 2 cells. I'll select this one which I want to partition, and I'll select this edge, and I will select this, I will partition this along this edge. Previously I selected that edge because that was a part of the cell, because there was only one cell. Now I am partitioning this cell, so I cannot take that edge because that is not a part of this cell. So I have to take this edge which is parallel to the previous one. So create partition, this is done. Okay, so now I have 2 partitions, and I will be defining smaller elements there, a little bit smaller here, and much coarser there. So for that I will go to local seeding, for which this is the button, okay. So local seeding, and I want to keep it regular, so I will take this edge, this edge, this edge, that edge, this edge, and one more, this, everything, and I will say by size 0.1. Okay, so you see this is how it is going to be, okay. I can select this one also, this one and this one, done, 0.1, apply, okay. And I can also mesh it region wise. So if you instead of clicking on this button like this, you just click and don't leave your mouse, then you see 4 other options coming, and there you have this one which is mesh region. So you can select small region to be meshed, but before that I want to see if I have described the type of element. So I want hexahedral elements. Hexahedral is that brick type of element. Oh, did I draw that element? Oh, I didn't draw it. No? So let us come back to whiteboard. Are you guys there? Okay, so if you look at the whiteboard, then the C3D8R element, R is just reduced integration, so it's basically C3D8 is. So in 2 dimension you have, this is your rectangular element, right? And the same thing becomes like this. It's a cuboid basically. So this is what C3D8R element is. So you have 3-dimensional element, that's why you have C3, then you have node number 1, node number 2, node number 3, node number 4, 5, 6, 7 and 8. So it's like a unit cell, okay, but depending upon sizes, it can be, instead of cuboid, it can be a parallelopipe, which is called hexahedron, okay. And what else? Yeah, so this is that element. And if you create, instead of linear shape function, so you see the shape functions are being linearly interpolated from one node to another. So if you want to create a parabolic shape function or higher order shape function, that would mean creating a middle node on each of the edges, right? So that is called C3D20R if it is reduced integration. So instead of 8 nodes, there will be 20 nodes, okay. So now you can imagine that instead of 8 cross 1, so 8 cross 8 of a stiffness matrix for one element, not for the whole model, for one element, 8 cross 8, you will be having 20 cross 20 matrix, okay. And then at the end you will have to assemble all these elements in one matrix. So if you have 20,000 number of nodes, so the global stiffness matrix will be of the order of 20,000 cross 20,000, okay. So come back to model. So here I want structured, meaning all the mesh should have a good continuity, so they should not be a big element next to a very small element. So structured and hexahedral. I don't want tetrahedrons, and hex dominated means you will have some hexahedrons and some tetrahedrons, and wedge is a wedge shaped element. Okay, so I want this. So that is done, and then I just will mesh this part because I have assigned local seeding there, so it looks like this, very fine. And you see 39,400 elements has been created. In each element you have 3 degree of freedom at each node, right? So just multiply it in with 3, a little less than that will be the total number of nodes. So if it is 40,000 elements only in this part, you will have 1,20,000 number of nodes approximately, and into 3 will be the degrees of freedom because you have u1, v1, w1, right? So at each node you have displacement in 3 directions, u1, u2, u3. So 1,20,000 into 3, 3,60,000 degrees of freedom. So your global stiffness matrix for just this part which we have meshed will be 3,60,000 cross 3,60,000 number of elements in one matrix. Okay, so this is how exponentially the size of the problem increases by decreasing the mesh size. Okay, and this is why people increase the mesh size. So now I want the element size to gradually increase as we go away from the center. So I have taken these 3 edges and I say done, and I want a biasing. Okay, biasing meaning from the center towards the edge the size should increase. Okay, so by default the arrow shows the direction in which the smallest size element should be. So I will just flip it all 3, and the maximum size I want to have like 0.5, and the minimum we will go to 0.1 because 0.1 is the size there. Apply. So this is how the seeding looks like, and then let us mesh this part also, and there is some weirdity somewhere because of probably, so we have assigned there, we have assigned there, and we have assigned here also, but it is, so it has to keep 0.1 there, and it has to keep, so it can keep 0.1 there. Why this is not so regular here? I do not know. Okay, but the element size is increasing. Okay, I think if I, what did I do? So done, and this is okay, this is okay, and meshing part was, so I take this, done. Oh, okay, fine. Okay, now I want the size to even increase to a larger extent at the end. So done, and now I want to increase it to 2.5, let us say, and the minimum should be 0.5. Okay, because we ended at 0.5 there. So apply. Okay, mesh this region. Yeah, so it will change a little bit to maintain, which is not good. This is not good. If we mesh the whole thing together, nothing changes. So our meshing is not very good. We may need to create a partition here also in order to make it good, because at the center it is somehow weird. So if I want to extrude this line, along which axis? Okay, so let me partition this face and take this one and partition it like this. Done. And then let it go through. So done. Okay. This one is also not partition, no? So let it be like that. How is our elements are defined, no? But here not. So done. Flip it. 2.5, 2.5. Mesh. What happened? Oh, this became further weird. Why? So if I begin meshing with this, what happens? Huh? Oh, so one cell. So here it is keeping it good, but there is a curvature in the middle. Why there is a curvature? Because of the curvature. Why there is a curvature, I don't know. Yeah, but curve on the curved side, it is like this, no? And then at the center, why it goes like that? Yeah, could be. Could be. So if we make it sweep, as one medial front, minimize the mesh transition. Okay, lead mesh. Now it is okay. So our algorithm was not correct. Now it is okay. So these two also will. No. So I have to go there and make it sweep, medial, minimum transition. This one we already have, right? No? Yeah. Okay. And mesh it. Then mesh this one. This will make it. Yeah, it is good, not bad. It is regular than last time. We're creating too many elements, so now it looks good. It is not looking that bad. To make it good here, I'll have to partition it further. But so let us deal with this. Let us go ahead with this. Okay, so meshing is done. Now we'll go to job. I hope I have done everything. So let me see. Field output request pre-selected default is there. Okay, so good to go. We go to job, set work directory. Oh, okay. So resolution issue. So it is there in the work directory. Now we create a job to 3D. I don't think it can start with a number, but I am not so sure. So 3D underscore damage 1. So let me give it 40%. I think because we have too many elements there. it might be consuming a lot of memory. So we have 15,800 plus 20,540 plus 336, 35,000, 36,000, 340, 36,640. So approximately 34,000 elements we have, which is not much. 34,000 is okay. So we are getting some warnings. Let me change the resolution again. So what warnings are we getting? I'm getting some warnings. 4,007 are distorted, either blah 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 blah. Okay, so some of the elements are not good because of meshing, but that is okay. So one calculation has been done. Oh, it is going fast. So, but it has to create like 100 points. If it reaches 0.05, then 50 points. So now there is a gap of 0.05 or 0.47, 0.43. Now 0.5, 0.05 is the gap. Okay. So it has reached its maximum increment size. So 20% calculation is done, 25% is done. So let us look at the results, how they look like. Some weird making is happening. And this is like something, but this is because our factor is too high. So it looks like this, and you see the stresses are higher, so it is not uniform. The stresses, the elongation will be uniform for some time, and then I hope it will start making. So if we go to, oh, that is what I missed. Right, so in the field variable we should have selected the damage parameter. So I'll have to kill this. Kill, yes. Go to field output, and here in field output we have to select some parameters. So for that you need to go to porous media. Porous media, because we are talking about voids. So we go to void volume fraction. Void volume fraction due to growth, nucleation, and then we have to take state where we need to select the status, which will define if the element is broken or deleted or not. So if it is 1, element is gone, 0, element is there. Okay. So these are the things which we have to include in our field variable, and then we can submit the job again. So did you guys understand anything on the boundary condition part and partitioning? So you should practice all those things. And so this pre-processing part, modeling part is done. Now you have to apply some brain on the post-processing part also. One dimension, sorry, axisymmetric 2 dimension में किया. How did we calculate the force? कितना force आएगा, उससे engineering stress कैसे आएगा? Now you have to do the same thing on 3D. So in 3D, how will you get the force? Where will you get the force? And how will you calculate the elongation? So the question you should ask yourself while thinking that where should I take the force or where should I take the elongation is that what happens in experiment. So you ask yourself this question, that where do you measure in experiment the elongation, and for force you have to ask yourself that where will the force come up because of my boundary conditions. So if you have applied a force somewhere, there you cannot calculate the force. You have to calculate, because the model tells you about the reaction force. Okay. So you think about this, and from this model, in your next lab report, you have to do this modeling with damage, and you have to find out the stress strain diagram, engineering stress strain diagram, and you have to plot that, and also write what you learnt about the damage parameter. Is this okay? Is this understood? Okay, so 40% calculation is done. Let us look at the results. And this is this. Oh, I think I made a mistake or what? I think I've refined something which is not at the center or what? No, but the stresses are higher there only, no? This is okay. But why it looks like that? Why it looks like upside down? Okay, let us see where the voids come up. If the voids are coming up above, I selected the void parameters also. Why those are not here? Did I not select the void? I did, no? So where is my input file? Is there? So ये क्या है? The log file, input file. VBF select किया, फील्ड आउटपुट में VBF सेलेक्ट किया, VBF ये सब तो है, देन एलिमेंटल should be showing. Where is it thinning? Everything is right because I am in stress. The plastic strain is high, so it should be there only. It is getting elongated so far uniformly. Why I am not getting void volume fraction? Because there is no void or what so far. So it is done, it's finished. It's finished. Job is completed. 2 millimeter. Why it looks like this? Okay, so that is the center part. This is okay because this part is moving, that part is not. So that is the center part. So refinement is on the right position, but I do not see the void volume fraction. Probably our amount of displacement is too low. Is that the case? Probably we have, so we have to see. So what we have to see is our failure strain was 0.3, fracture strain was 0.3. We need to decrease that so that the damage starts a little earlier. So we need to decrease that. We need to start the damage a little bit earlier. So instead of 0.3, let us keep it 0.05 and 0.05. Okay, and now let us see what happens. So oh, V wave is not available. Oh, it's because of reduced integration. I forgot. So we have to change it to full integration, because in reduced integration void volume calculation cannot happen. So we have to go to mesh in the assembly module and go to the, but there also we can do something, because void will be coming up in the lower area only. So the two partitions which we have made, luckily we can choose those only, and there we can create full integration, and the rest of the places we can deal with reduced integration. So now let us see. Also, there was no need of changing fracture strength. It was because of reduced integration. And now it will be damaging too early, I think. Yeah, so this is VWave is not available for material for element type C3D8 also. Why? This. Why is this? C3D8R and C3D8, it is not available. Void volume fraction. Why? Okay. So maybe they have changed it to some other variable. Void volume fraction due to growth. So if I go there, then we have shear damage, bonding of failure. No. These should be defining void volume fraction. Oh, okay. Okay, so I forgot. So void volume fraction is for a different damage model, which is porous plasticity. So we cannot use those. So we cannot use porous media because we are using a different damage model. We are using ductile damage model, and this void volume fraction and other things are used in porous plasticity. So in our model we have defined a continuum damage thing instead of simulating voids. So for that we have to select stiffness degradation parameter, which will tell us. So stiffness degradation factor is actually telling us about the damage parameter, right? And then we can have I believe we can have tensile damage and compressive damage, and that's it. Okay, so SDEG is the parameter which should be telling us about our damage variable value. Are you guys there? that should be fine. So what we discussed today was also in alignment of the project topic which I have given, right? So we discussed something about the ductile fracture, which is your topic for the project. So are you guys doing some research on that? No, you don't have to make equation. Who told you have to make equation? You have to make mathematical model. मैथमेटिकल मॉडल में तो आपको वो करने की जरूरत नहीं है, फाइनाइट एलिमेंट एनालिसिस. Is this being miscommunicated? See, in those MM308, MM311, we are giving one topic, right? So Dr. Prince will be giving you one topic, I have given one topic. For that topic, what I want you guys to do is, and you please revisit that part where I have discussed the topic, is that you have to mathematically model the situation. So I believe I have shared an example, like a brick is slipping on a wedge shaped thing which you have done in your school days, right? So you just make a free body diagram and then you have an equation following Newtonian's mechanics which can accurately tell you that with what velocity the brick will slip, right? Keeping all the friction coefficient and everything in your calculation. So similar thing which you have to do in order to model the ductile fracture event. And for ductile fracture event, what are the things which you have to consider? You have to consider how it happens. So it happens via voids, when they form, when they evolve, how they evolve, when they fail, and all those things. So you don't have to do finite element simulation. Okay. You have to simply make simple rules, simple laws, simple equations and tell that this is how I will tell that the damage, or this is how I can define the event of ductile fracture in the material, which will be a function of yield stress, UTS, failure strain, strain rate, stress triaxiality, this, that, whatever you want to take into your consideration. That is what, and there is some marks on novelty, significant amount of marks is on novelty, some marks is on your presentation style and other things. And please watch, I have shared the playlist for the last semester course, no? So please watch their videos where they have presented their results on their project topic. Okay. So when you look at their results, no, their presentation, you will know that you don't have to do finite element simulation or so you will have clear idea what you have to do. Don't get confused. ऐसा मत करो कि लास्ट एंड सेमेस्टर एग्जाम के 2 दिन पहले नहीं हो पाएगा और इस पे बहुत अच्छा अमाउंट ऑफ मार्क्स है, ठीक है? तो जो लूज करेगा वो अच्छा खासा लूज करेगा. सो डोंट बी इन योर डिल्यूजन दैट यू नो इट विल बी वेरी फाइन और this, that. आप एक आइडिया ले लो, you have certain idea, your seniors didn't have any idea कैसे होगा क्या होगा. So if you have this thing, no, you use it, you go and watch that their presentation and you also see that on what things the questions has been asked and what will give you marks and how to go in this direction. You will get a lot of ideas from there. You get it? Okay, so let us see if our sample shows anything. I don't think it is. No deletion of element, nothing at all. It is just getting elongated. Stubborn sample. STG 0 value. That means there is no damage. So we need to pull it further. So we'll try one more case, and then if it doesn't happen. So there is no degradation. That means there is no damage is not coming up. It's not even starting. That means our criteria is too soft. Our damage is not even initiating. Why? Maybe our strain rate is too high. Because I don't think fracture strain is too low. One thing could be our displacement is too low. But in metals 2 mm is good. So what if I make it independent of strain rate, then what happens? And also let me increase the displacement a little bit. Instead of going to 2 mm, go to 10 mm. Then you must break. And then job, submit. Okay. %. No degradation. And usually when damage creeps in, the increment cannot be so smooth. So it has attained maximum time increment. Let us see what happens in the next one. Next one is taking some time. not converging? Which is a good sign. So it has converged for a smaller value. That means it is not so smooth. That means something must have happened. So it will take some time. The time is 0.24125, which is where we are. But the calculation for 0.25375 is also done. So why we are not able to see that? Yeah, we are there, but still no degradation is showing. So we have to see how much strain we have reached. So plastic strain is how much? It has reached 0.13. Our initiation was 0.0. How much was our initiation strain? Initiation strain was 0.05. That is long back. This plastic strain, or what is equivalent plastic strain? Is 0.13. So just double of what we had. Right. There must have been some degradation. Nothing. It shows nothing. This I don't understand why. So we have crossed yielding. We have reached 600 something, which is स्ट्रेस यहाँ पे ज़्यादा क्यों है? स्ट्रेस तो यहाँ पे ज़्यादा होना चाहिए था. Now it is okay. Now it is okay. Now it is okay. So stress has increased very fast. So there must be is there some thinning? It looks like still no value of degradation. It looks okay. The stress profile is okay now. There is still no value. I don't understand why. Stiffness degradation तो होना चाहिए as soon as you have strain reaching that value. So plastic strain is also high here. How much is the plastic strain? अच्छा, now it has gone to 0.3. हमने दिया 0.05. 0.05. So 0.3 is too much already. Then why not? But it is necking now. You see, it is necking. So if I enhance this to a factor of 2.5, it will be clear to see that it is necking. Wait, I don't know why it is not showing stiffness degradation parameter. So डैमेज पैरामीटर का वैल्यू क्यों नहीं दिखा रहा है? कैलकुलेशन में तो है, अदरवाइज देयर विल बी नो नेकिंग एवर. So STG, I think there is some problem with this guy. But the calculation is saying, so I'm sure element will get deleted also at some point when we reach failure. It will get deleted also. So you will see that elements will start deleting. I hope that will happen. But I don't know why that thing is not coming up. Status SDG is still 0. SDEG, if we could see, we could tell that if that reaches to 0.9 it will fail, but it is not showing. I don't know why it is not showing. तो फील्ड वेरिएबल में तो SDG डाला है. हिस्ट्री का तो कोई लेना नहीं है. So this is in step 1 whole model. Every increment you have asked for SDG, then why not stiffness degradation का वैल्यू दिखाना चाहिए. Volume thickness 409 years. This is what it is. Why it is not showing it? I don't know. So you have somewhere SDG is here. It's there. It's not showing. So ये क्या हो गया इसका? इसका वैल्यू ज़्यादा जा रहा है. Now it is going beyond. So still 0. So let me, this is 2016, but while the job is running, I don't think I can open it anywhere else. So we can see from here ODB field output, and here if I select stiffness degradation and select an element, नोड पे वैल्यू दिखा रहा है. ठीक है, नोड पे देखते हैं. तो सेंटर नोड पे क्या वैल्यू है? कुछ तो वैल्यू होना चाहिए. Done. Save. Okay. SDG value 0 0 0, still 0. Still 0. Yeah, this cannot happen. 0 में नहीं कैसे होगा? So the amount of failure it will take is how much? 90%. 90%. How much is the hydrostatic stress? So pressure 700. The pressure is minus 798. The pressure is positive. The pressure value is positive and the triaxiality value is negative. So we are not in that space yet. We are not even in that space yet. So pressure is positive. So minus P by Q will be a negative value. So we are not even in that space yet. So in stress triaxiality, you have to go to minus 200. Yeah, but even then it could be so minus 700, no? So minus 5000 कर देते हैं इसको. But ratio तो उतना होगा नहीं. 700, 800 divided by Mises का जो value होगा, it cannot go to that value, but it will go to negative. So 200 is okay. Maybe this space is the plastic effect of equivalent plastic strain rate. So let us see how much is that. So our plastic DEQPS, so PEQ is 2.64 now, and so we can check it in one element. So integration point, edit. Let us take one element here. This is a big element, and say okay. So what was it? No. क्या वैल्यू लिया? नहीं. Equivalent plastic strain लेना. So equivalent plastic strain. Save. So it should be here. So कितना है? This is at the end, it is going 2.5 to 2.46. So the difference is approximately 0.05, 0.04, then 0.02, and so on, in the time of how much? So it is going from 2.4 to 2.43, so 0.03 approximately in a time of 0.004. So 0.004 is the time, and the change is 0.03. 3 divided by 0.004. So the plastic strain rate is going to 7.5. Plastic strain rate is going to 7.5, and initially it's 0.5, 0.55, so 0.05 in a span of 0.01. 0.05, 0.01, so 5 to 7.5. So it remains in that range, strain rate. So इसका भी space बढ़ा देते हैं so that it becomes independent. And fracture strain, I believe it's too small, so we have to make it 0.2, 0.2, and we have to give, yeah, so this I forgot. So displacement, we have to give some fracture energy. So evolution we didn't give, so there was no evolution, so that was the problem. So linear is okay. So fracture energy I'll give. So for metallic materials it should be how much? 50 is okay. So fracture energy is actually Griffith's energy, and damage initiation, damage evolution, and fracture criteria is given. So now it should work. So I'm now considering that it was the damage just initiated, but it was not evolving because the evolution part was not made clear to the model. So I hope it should, now it should work, but then something else also can be forgotten. So Yatin, are you there? Okay. So a few ways are there. Okay. Okay, so let us leave it for 5 minutes and see what happens. ले लो. This is Vedant, not Sachit. Screen is not visible. Why? Is it visible now? Hello? Is it visible now? Oh, internet is gone. Good, good. Can you hear me? Can you hear me? Yeah, there was institute internet connection was gone. Still we have not proceeded much in time. And now you see the damage variable value is here. Can you see the screen? So this is the damage parameter which is started from a very small value and the maximum value is at the center, which is still 0.25. So this will go to 0.9, then the element will get deleted. Okay. So this is where it is started from. So in this frame you see there is 0 value, and then now you see some value, right? And the red one will be somewhere, but the yellow one is 0.01. So our starting point is how much? 0.05, no? So if you look at equivalent plastic strain, so that has a value of 0.2. So and just before this, still there. So damage must have initiated when the value was 0.05. So at this point of time. And after, bolo. Yeah, that happens. Sometimes that happens. So that is already clear, no? So when you go for washroom, you write it in the chat box. No, it's okay, nothing to be sorry. So now you see the damage is coming up. So now it has gone to 68.7% here, and a element has been deleted. Do you see? One element is gone. Can you see this? One element is gone, and if it proceeds further, so that element is, and if that element remains there, like now, so 2 elements are deleted. So if you look at status, it will be 1, and as soon as I go there, these 2 elements must have the status value of 0, but you cannot see them because they are deleted. Because we exercised that option, no, if you remember, element deletion, yes. So ये 0.3396 पे है, and because of damage the calculation has become not so easy. So initially you will see that it has attained the maximum increment size of 0.5 when there was no damage, nothing, and then as soon as damage comes up, the calculation becomes difficult, and it looks like it cannot take it because the increment size has decreased to a very small value. So that is happening because these elements are not so good and they have extended to a very high aspect ratio, and you see more and more elements are getting deleted. So this is simulating necking as well as fracture, right? So everything works good. If so, we should not keep elements like this. We should keep proper meshing instead of this curvature. And also what happens is, like, see, the fracture in real specimen will not be happening like this, no? This is understood, no? So you will never see a metallic material which is ductile which will have a hole like this at the center. So here we are mesh dependent in our solution, because at least it can delete one element, it cannot delete half element, right? So वो shape factor will come in. So if the element is of hexahedron shape, it will create a hole of that shape only. So in order to make it as accurate as possible, what you have to do is you have to make very fine mesh, very fine mesh. Only then you will be able to simulate the ductile fracture phenomena. And so what you have to do is, if you plot now the stress strain diagram for this model, so now the engineering stress strain diagram will be decreasing, because you are able to simulate the necking as well as fracture also. Okay, so if you so if you look at like this, then you see that necking is also happening and fracture is also, the stress strain diagram will be going down. Okay, क्लियर हुआ कुछ? थोड़ा बहुत क्यों? So what you have to do is you have to do this modeling, और जो हुआ वो आप रिपोर्ट करेंगे, and results से, so from your 3-dimensional damage model you have to calculate the engineering stress and engineering strain like we did for our 2D model, axisymmetric model for elastic plastic case. Same thing you have to do here, and you have to plot that engineering stress strain diagram in your lab report. Okay. ठीक है ना? Next week? So 18th, when is the mid-sem starting? From 27th, no? Wait, 25. When do you want to keep your Viva? मिड-सेम कब खत्म हो रहा है? फिफ्थ मार्च को. That will be too late. 25th को तुम लोग का एग्जाम है कोई? Okay, so we have to see the academic calendar. Anyways, हाँ हो सकता है. हाँ बिल्कुल हो सकता है. So mid-semester examination, mid-semester project evaluation. So there we will have this CP projects. Last date of showing of marked answer script March 11. Then class committee, last date of audit withdrawal, blah blah blah. Okay. So last date of showing of the result is March 11. ठीक है. So March 11 के पहले कर सकते हैं I think. I think we can do it before March 11 sometime. So so till 4th your midsem exam is going on. हाँ ठीक है. तो 4 से 11 के बीच में, 11 छोड़ो 10 के बीच में मेरे को कोई एक डेट दे दो इसके लिए, वाइवा के लिए ना. ठीक है. ठीक है. इज इट ओके? सो डिसाइड करके मेरे को पहले ही बता दो, सो दैट यू डोंट पुट एनी अदर अपॉइंटमेंट देयर. और लैब रिपोर्ट सबमिट करो. देन यू सबमिट इट ऑन, व्हेन कैन यू सबमिट इट? सबमिट इट ऑन 11th. दैट इज फाइन ना. सो 11th को सबमिट करो. ठीक है. सो बट यू गिव मी डेट फॉर वाइवा, फिक्स इट and give it to me. Huh? What else? Okay, and keep thinking about that project part also, because end sem में ज़्यादा time रहेगा नहीं, and we will be taking presentation also at the end. So उसमें थोड़ा मेहनत करना पड़ेगा. If you think of something, then discuss. We can discuss. If you haven't started, what will we discuss? Okay. Anyways. So we end this session and we will meet for mid semester viva, right, before lab I think. Okay then.